In this lecture, we talk about how you can represent AC voltage sources and current sources by complex numbers. So we know that an AC supply, whether it's a voltage supply or a current supply, that's oscillating sinusoidally can be represented by a phasor. And of course, that phasor is just a sort of a vector that has some length associated with it, which is just the magnitude, amplitude of the oscillating source, and then the angle that's associated with it. And so in phasor notation, we could write this in terms of that polar, I guess the polar form, which would be the length and then the angle that's associated with it. But this also looks very similar to complex numbers. So there's sort of three different ways that we can now represent an AC source. So we start off with our AC source, and it's written as a sinusoidal varying function. We can, of course, draw the waveform for that, and in this particular case, the phase shift is 40 degrees, so it would be shifted to the left by 40 degrees, and it would have a maximum value of 200 volts, or an amplitude of 200. And then we know that we can also represent this in phasor notation as a phasor that has a length of 200 and an angle of 40 degrees with respect to the horizontal axis. And so basically we can take a picture that we would represent in a sinusoidal way, and we can transform it into our phasor notation. So anything that we have that varies sinusoidally, we can then represent in this phasor notation. Now the one thing that's missing from the phasor notation is the angular frequency. So that actually is important in a lot of AC circuits, and we'll talk about that a little bit later. So sometimes that frequency could be given in the problem or in the schematic diagram. So suppose that I had two AC sources. So here I have a source E1 and E2. The first source is varying sinusoidally with a frequency, an angular frequency omega. It has no phase shift, and it has a maximum value of 10, versus the second one that has a maximum value of 15 and is phase shifted by 60 degrees. And we want to know what is the total voltage across these terminals if I have these two alternating sources. And so it turns out that you can sum the waveforms point by point. And so if I look at each one of these, so I have the first source here that's represented by the waveform, and it's not phase shifted. And then I have the second one that has a maximum of 15 and is phase shifted to the left by 60. And I have that one. At any given instant in time, I can figure out the total voltage by adding the voltages together at that time interval. So in a waveform type of notation, that means that I would have to add the values together. So the easiest one, of course, is to start off here. I would have to add 0 at time t equal to 0 to whatever the value is for this voltage supply at time t equal to 0, which happens to be 13. So when I add those two values together, that gives me the total, and the total is represented with green here. And then at 90 degrees, I could add them together again, and so on at different time intervals. But one of the things that's really important is to notice that when you add two sinusoidal varying functions that have the same angular frequency, so the omega is the same for both of these, that you get a new sinusoidal varying function, and it has the same angular frequency as the two that were added together. It has a different amplitude associated with it. And so we're interested in how could we represent this new total sinusoidal varying function. So what I'm going to do is I'm going to go through this the long way, and I'm going to tell you up front that this is never the way that you're going to do it. But for the purposes of just showing you why we can do what we're doing, I want to show you that the two methods are equivalent, and then we're just going to use the easier method. So this method will not be used when we're solving problems. So we start off and we have this, we have these two sources, and we're going to add them together. So I want to add these two sinusoidal varying functions together. And I want to represent this as a single sine function. So how do I add these two together? Well, the first thing is that I can't just add 10 and 15 because they're not the same sine function. So I need to take the sine omega t plus 60 degrees, and I need to use one of the trig identities to separate out these two angles here. So I know that sine of theta plus phi is cosine of theta sine of phi, sine of theta cosine of phi. And this is just one of those trig identities that we learn in some of our math classes. So if I go ahead and I use that identity, my first term stays the same. My second term, I would have cosine omega t sine of 60 plus sine omega t cosine of 60. So now what I can do is I can collect like terms in terms of the sine omega t and cosine omega t. So I have terms that have sine omega t in them would be 10, and then there's also a term here with sine omega t which has a cosine of 60 and a 15. So collecting like terms with sine omega t, I have 10 plus 15 cosine of 60, and then collecting like terms that depend on cosine omega t, I only have a term in the second part here, so it would be 15 times sine of 60. Now, my goal, of course, is to be able to write the addition of these two sine waves as a single sinusoidal varying function. So what I'd like to be able to do is to write this back in the form of the trig identity where I have a combination of sine and cosine functions, because I know that I can write that as a single sine function. So what I'm doing is I'm collecting the sine omega t and the cosine omega t, and I'm keeping those in there. And then I am replacing what's in front of those with a new phase angle and some constant. So the term that's in front of the sine omega t is now some constant times cosine of some angle phi, and the term that's in front of the cosine omega t is now some constant times sine of phi. I can call them anything I want, and let's just see if this works. And so if this is true, then the term that's in front of sine is going to be the term, these two terms have to be equal that are underlined in red, and the two terms that are in blue are going to have to be equal to one another. And if I can manage to do that and say that they are equal, then that means that according to this trig identity, that this total voltage is equivalent to some amplitude, C1, because I can factor out the C1, times sine omega t plus this phase shift. So basically what I've done here is I've shown you that you can take two sinusoidal varying functions that are not in phase with one another, and you can replace them with a new sine function that is shifted from the original sine functions but has the same frequency. But we need to figure out what this constant is, here C1, and we need to figure out what this phase angle is. So starting with what we know that C1 times cosine of the angle is equal to this value that was out in front of the sine term, and I know that C1 sine of phi is equal to that other term. So I can square both of these equations. So I can take the left term here and square it, C1 squared cosine phi squared, and I can add it to C1 squared sine squared. So I'm going to take this term and I'm going to square it, and I'm going to take this term and I'm going to square it. That's these pieces. And that's going to have to equal this term, 10 volts plus 15 cosine of 60 squared, plus 15 sine of 60 squared. I can factor out the c squared, and I end up with cosine squared plus sine squared, but I know that cosine squared plus sine squared is equal to 1. So the left side of this expression just becomes c1 squared. And now I can just put numbers in, right? So I can use my calculator, and I can take this term and I can square it. I can take this term and I can square it, and I get 475 volts squared. If I take the square root, I end up getting that the constant C1 in this expression would be 21.8. I can figure out what the angle is here by using the idea that tangent of an angle is sine over cosine, And I can certainly multiply both sides, top and bottom, by C1. So C1 sine over C1 cosine. But I know that C1 sine is just 15 volts sine of 60. And I know that C1 cosine is just the other term. Those are just numbers. I can plug those numbers in and I get 0.7423. So if I want to know the angle, I can take the inverse tangent of that value and I get 36.6 degrees. So I've started off with my two sinusoidal varying functions. They are not in phase with one another. And I can add them together. And when I add them together, I can get a new sinusoidal varying function that has the same angular frequency but a different phase angle. And I found that the amplitude of this new wave is 21.8. And I found that the phase angle was 36.6. So that was a lot of work to get to that answer. And certainly if you had a whole bunch of sources, you would not want to try to go through all this and using these trig identities. So there's a much easier way to do that. And the way to do that is to use phasor notation. So if we think about these two sources in terms of phasors, we can write them. Of course, the first one would be 10 volts with an angle of 0, and the second one would be 15 volts with an angle of 60. Now what I can do is I can treat these as complex numbers. And so if I treat these as complex numbers, I can write them in their complex form by using the fact that the real part is just, for the first one would be 10 volts times cosine of 0, which is 10. And then, of course, there's no imaginary part because this would be sine of 0 and that would be 0. I can do the same thing for the second one. So 15 times cosine of 60 would be the real part, and 15 times sine of 60 would be the imaginary part. So what I'm doing is I'm taking these sinusoidal varying functions in phasor notation, and I'm treating them like complex numbers. And so now I can add those two values together. And so if I add those two values together in complex form, I know that I would add the real parts together, and I would add the imaginary parts together. So if I add the real parts together, 10 plus 15 cosine of 60, I get 17.5. And then if I add the imaginary part, I have 0 plus 15 of sine of 60, I get 13. I can take that representation in complex form and I can write it in polar form. And if I convert that back into polar form, which we know how to do now because we've studied complex numbers, the magnitude would be 17.5 squared plus 13 squared square root, and I get 21.8. And if I wanted to figure out what that angle was for this complex number, I would take the inverse tangent of 13 divided by 17.5, and I would get 36.6. So because we're using this phasor notation, I can now write that equivalent voltage in a sinusoidal form as having an amplitude of 21.8 sine omega t plus a phase shift of 36.6. This is exactly what we got when we went through this the other way using the trig identities and converting everything back and forth. So this isn't a rigorous proof, but I wanted to show you that using complex numbers to represent phasors is an appropriate way to add sources that are varying sinusoidally, adding voltage supplies, adding current supplies, dividing current and voltage, or whatever we're trying to do to figure out the unknown in a particular problem. So here's our picture with, again, going back to those two sources. There's the waveform method where we add them together, and then here is the phasor notation where we can add those two phasors together, and we end up getting our total voltage, and of course everything adds up appropriately so that at time t equal to 0, the phasor notation is representing what the values would be. The projection on the vertical axis is telling us what the values would be at time t equal to 0. One of the things that most textbooks do is to actually use the root mean square value instead of the peak values in phasor notation. So in our time domain expression and our waveforms, we would write a supply as being the amplitude times sine omega t. And so typically in phasor notation, which is also called the frequency domain, we would use the root mean square value for the length of that phasor, which is just the amplitude over the square root of 2 and then the phase angle. So we would write it like this. We haven't been doing that up to this point, but I will start doing that from here on out because that is a traditional way to represent phasors. If you forget to do it that way, it's not the end of the world, but you should try to remember to do that from here on out. One of the things that I did want to point out is that Kirchhoff's voltage law and Kirchhoff's current laws are still valid with sinusoidal varying functions. So, you know, if we had two voltage supplies that were next to one another and they were in series, we could add them together just like we did in the previous example. And if we wanted to find the current in a circuit, and we might need to use the equivalent of sort of Ohm's law. And so from here on out, when we're analyzing circuits that have AC involved, we're going to use phasor notation, and we are going to use complex number notation to add, subtract, multiply, and divide.